Algebra 2, Unit 4, Section 6. Now, this is actually supposed to say operations with complex numbers. This was the same title as the last slide. See here, imaginary complex 4, 5. 4, 6 is supposed to be operations with imaginary numbers now that you have learned about them. So let me change that to operations with complex numbers. And, really what we learned in the last lecture, most importantly, the powers of I and how they are related to 1 and negative 1, I and negative I, and simplifying negative radicals. We're going to be using that here, and we're also going to be using our calculator to solve some of these things. But we're going to work with these just like if they were, regular, polynomials. Like if this was 5 plus 2x plus 7 minus 3x. Like if these were x's instead of i's, that's basically how you proceed. But in the end, when you have a I with an exponent of 2 or something, then we can, evaluate that for something else. As mentioned yesterday or in the previous class or lecture, we always do a plus bi form. So you notice that this is like 5 plus 2i. It's not 2i plus 5. And if in the end we ever get a result like 2i plus 5, we do need to rewrite it to be 5 plus 2i. I have seen problems that were designed specifically so that after the work it was backwards. And you had to know to reorder it. Basically, we always want I to be the last thing written, the furthest to the right of the expression. So adding expressions, this is just combining like terms, and here, we're just adding, so there's no distribution of anything, and 5 plus 7 is 12, and 2i minus 3i is negative I. And that's as far as this can go because there is no power. I mean, we know I to the first is I, so there's nothing I can do there. What we're really looking for is at the end of these, if we have something that's I squared, I to the third, I to the fourth, and that is what we can then simplify further. Here you're subtracting. Just remember that when you subtract a polynomial, you have to subtract every piece of it. Another way of thinking of that is distributing a negative 1. But you got to distribute that negative throughout. So this is going to be minus 7 and minus a negative 3i. And when you subtract a negative through keep change, it ends up being positive 3i. Or you could think negative 1 times negative 3 is positive 3i. And combine that with these, and so I have 5 minus 7 is negative 2. 2i plus 3i is 5i, and again, that's as far as that will go. Now here we're doing a little distribution. The working with exponents, again, if this was 5x cubed, 7x squared, I would do the same thing I'm going to do now. I'm going to multiply, and when I multiply the coefficients, 5 times 7 is 35. Nothing special there. And then I to the third times I to the second. When I multiply a common base, I add the exponent, so that is I to the fifth. And then when I distribute that in here, 5i cubed minus 2i will be negative 10i to the fourth, because this is to the first. And again, I'm adding exponents. And now this is something I can simplify. I to the fifth and I to the fourth, what do they work out to be? Again, we know we could use our calculator for assistance here, but it's helpful to understand and really know the powers of I, because there are going to be some problems where the calculator can't do it all for you. So I to the fifth is just equivalent to I because it's 1 more than a power of 4. So it's like I to the first. I to the fourth is a power of 4, so that's simply equivalent to 1. And so this comes out to be 35i minus 10. And this is a prime example of what I was talking about, a plus bi form. You can't reduce it any further, but that can't be your final answer. You have to write it as negative 10 plus 35i. That is a plus bi form. That would be the final answer. And it seems silly, but that is, I've seen many students on a question similar to this on a Regents exam lose a point because they wrote this as the final answer. But remember, this negative belongs to that 10. It stays with them. This 35, when there's no sign in front of it, means it must be positive, so that's why it's a plus. But that's your final answer. Now, there was another way to do this question. I could have reduced first, like 5i cubed. I cubed, I know, is negative I. And so that's negative I times 5 is negative 5i. And 7i squared is negative 1. So that's 7 times negative 1 is negative 7. And minus 2i I can't do anything with yet. But then I can distribute in, and I would get Negative 5i times 7 is 35i, and negative 5i times positive, I might as well write it, positive 35i, and a positive 10i squared, but again, I'd have to reduce that 10i squared to be negative 10. And so I get the same thing. So you can reduce your powers of I first and then distribute and stuff, or you could wait till they're, all multiplied out. I suggest waiting till it's all multiplied out because then you only have to reduce powers of I once. Here I reduced them to get this, and then I had to reduce them again later. So I would just, wait until you're all multiplied out to reduce your powers of I. Here, this is FOIL distribution, whatever you want to call it. But again, it's a binomial times a binomial. So I got to distribute all of these terms into all of these terms. Since it's 2 by 2, I'll end up with 4 terms, but then I have like terms from there. So 3 times 5 is 15. 3 times I is 3i. Negative 2i times 5 is negative 10i. Those are like terms that will be combined. And negative 2i times I is negative 2i squared. And two things, I can combine the like terms here, and I can reduce this term. Remember, the most important thing to remember is that I squared equals negative 1. And so multiply this out, it's really negative 2 times negative 1, which comes out to be positive 2. And then that's a like term with the 15. So in the end, I'll have 17, and then these combining like terms in the middle to be negative 7i. Last one, here we have a binomial squared, and you could write it as 5 minus 2i times 5 minus 2i and do exactly what we just did over here. Or you could do the shortcuts, and the shortcut is the mental shortcut for a binomial squared. It's a pattern of square the front times each other but double. So times each other would be negative 10i, double it to negative 20i, and then square the back. And negative 2i times negative 2i is positive 4i squared. That I squared, this is going to end up being negative 4 because I squared is times negative 1. And 25 minus 4 is 21 minus 20i. Now I want to show you that all of this work can be done on the calculator. Let me give you that last example, for example. So if I put in parentheses, oops, don't want to make that too big. Now, to be safe, it's good to use IPART, but none of these exponents are really larger than 2 or 3 or 4, so you probably don't need to use IPART, but, IPART is something you can do. I'm going to try to do it without 5 minus 2i, close the parentheses, square it, and there it is. There's our answer. So why not just show that? Well, because the people who made state exams got smart. And they said, well, this they're just going to type into their calculator. But if we make it something like 5i minus 2x squared, the presence of the x eliminates the ability to type it into the calculator. So here we have no choice but to do this work. That's why it really is helpful to remember I squared is negative 1 and know how this procedure works. Some of it, yeah, you're going to be able to just type that into your calculator. But they will throw an extra variable in there to make it a little bit more challenging. So let's actually do this question here. 5i minus 2x squared. So square the front. 5i times 5i would be 25i squared. Times each other doubled will be negative 20ix and plus 4x squared. This is the I squared piece, so that's times 25 becomes negative 25. So when I put this all in proper order, remember that's exponent descending order, this is going to have to go first, second, and third. And so it'll be 4x squared minus 20ix minus 25. And that I can't do on the calculator because the x plugged in there. If it was just 5i minus 2, something like this, that would be no problem. So again, there are calculator shortcuts, ways to check your work, but sometimes, even if this was a Regents question, the answer would only be worth 1 point. The work would be worth, another point or 2. So you do need to show the work here, but the calculator can check it for you, except, like I said, they'll make it a little bit more challenging by throwing in that extra variable. All right, but that's operations with complex numbers. It's no different than operations with regular numbers. Just in the end, when you have i's with exponents greater than 1, you're going to have to reduce that to either be negative I1 or negative 1. And then always look for like terms, and don't forget, when it's a plus bi like this, I has to go second. All right, So that's it for operations with complex numbers.